Hi, in this video, we're going to talk about algorithm performance and show an example of it. So we know algorithms are useful because they solve problems. So what are the most important requirements, the most critical requirements of an algorithm? Well, the obvious one is the algorithm must be correct, right? It must do the right thing, and it's useless if it doesn't give us the right answer for the problem we're trying to solve. Now, the second thing might be slightly less obvious, is that we must be able to run the algorithm given the amount of resources that we have. So one kind of a famous example of the kind of the opposite of that is that you might have heard of all these fancy quantum algorithms that can run so fast that they can say break all the security cryptographic algorithms of today. However, I mean, most of our data that are encrypted, they're still safe from these quantum algorithms. Why? Because quantum computers don't exist. So all these fancy quantum algorithms, we cannot run them, right? So it's important to be able to run an algorithm given the resources that we have. Now, when we talk about an algorithm's resource, they generally fall into two very broad categories. One is algorithm needs time, right? And these time they're usually expressed in terms of CPU cycles. It used to be just CPU cycles. Nowadays, there are GPUs, the graphic processing units that can do a lot of calculations in parallel. And then in the last few years, there are these neural processor units. So all of these processors, they take time to compute results. So time is one resource, space the other resource. So any algorithm, it will take up space to store all of its data. So space in terms of memory space, disk space, etc. That's another very important resource for an algorithm. There are other resources such as kind of network bandwidth in today's internet connected world. But all these other resources usually just kind of affect either the time or the space. And for this class, mostly we'll focus on the time aspect of an algorithm. So what an algorithm does in kind of a high level view is that given some inputs, it gives us some outputs. And for most algorithms, it's usually the case that the more inputs there are, the bigger the size of the inputs are, the more time it will take to process all the inputs and yield the desirable outputs. Then the interesting question becomes, how much more time does an algorithm would take when there are more inputs? So in other words, what is the rate of growth of an algorithm as a function of the size of the input? So this is called the time complexity of an algorithm. And to kind of study the performance of algorithm in kind of a more formal ways, we usually have kind of two notations. One is just n. N is usually just the size of the inputs, such as if the algorithm has to process a list, the number of elements or items in the list. Then to denote the time that the algorithm needs to process all the inputs, then we use the notation t of n, and that is just a function of n. So to measure performance, we really just kind of want to know what is the function t of n. So let's look at an example of an algorithm and its performance. So this is our version of the Python's view and max function. We've seen it before. Basically, we look through every item in a given list and find the largest one, right? Now, remember the fact that, yes, we have to look at all the items in the list. So if let's say the list has n items, and we measure that it takes x seconds to go through all n items. Then it's reasonable to think that if the number of items become twice as many, 2n, then it will take twice as many seconds, 2x seconds, to look through all of them and find the biggest. And the same thing goes for 3n items, then it should take 3x number of seconds, and so on, right? So at least in theory, and by just looking at the algorithm, the time function for this function, the time t of n for this function, for the largest function, looks to be just kind of proportional to n, which is a linear function. Okay, so that's in theory. So let's actually try to measure the performance of the function. So in order to measure performance, we can use a standard Python library called time. One of the functions that time provides, or method time provides, is called the performance counter. It gives us a value of a high resolution performance counter on your computer, and it's the unit of this counter is actually expressed in floating point seconds. So that's very convenient. So before we run this function, we take a time, and then after we run the function, we take the time after it's done, and then we take the difference between these two times, and then that should give us a fairly good idea of how long this function takes. Okay, so we can run this. I've already written this out. So if we run this, in this case, for the list of 4 items, it takes really like no time at all, pretty much. I think this is on the order of 3 microseconds. So, but that's reasonable given how small the list is, right? So the next thing we can do is we can actually, let's have a larger list. I'm not going to type out a larger list myself. Instead, I'm going to enlist random. So I generate a list of random numbers here, and that the number of random numbers is to be 1 million exactly. And I'll just run the algorithm. So I'll do the same measurement. Okay, so let me do that, and it's taking a bit of time. So as you can kind of see, the duration that is printed out here is about 0.05 seconds. So that's about 50 milliseconds. Now it actually felt a lot longer than that because generating random numbers, generating a million of them takes quite a bit of time. But actually looking for the largest one among those numbers, it's still fairly quick, but it takes a lot more time than before. Okay. Now, so as we said, the performance, or the T of n we're interested in, is, when we increase the size of the input, how does T of n changes? So let's actually vary the time of the input size and do a measurement here. So I'm going to comment out this line of code. I've already written it up. It's, oops, I'm going to show the, so this is basically exactly the same code as before, but instead of hard coding a count to be 1 million, I'm going to go start with 1 million incremented by 1 million every time, go all the way up to 4 million, I believe. I'm not going to run this because this takes a bit of time. You can try it yourself. I've already ran it before, and this is kind of one output that I have here. Now, so it's worth looking at that as the size increases. As I said, the size increases by 1 million every time. The first time it takes about 0.05 seconds, then the second time it takes 0.1 second, and then takes 0.16 second and 0.2 seconds. So every time the size is incremented by a million, the time increased by roughly 0.05 seconds. So that's kind of a hallmark of a linear function, right? Okay, so if we plot this out on an XY graph, with the y-axis would be the duration and the x-axis would be the size of the input, then it looks, well, not quite a straight line, but pretty close to a straight line. So this, again, kind of matches our theory that the t of n as a function of n is proportional to n. So we can almost write t of n equal to n. But then if you look at the numbers, well, that's not really quite true, right? So if you say, n is a million to start with, t of n should be a million, but it's 0.05. So what it really is that a t of n is a constant times n. Now, the precise value of c, as it turns out, and I'm sure it will make very intuitive sense, it's really not important. The most important part is that it's proportional to n, right? So that, t of n is a linear function. Now, if we look at this again very closely, even assuming there is a there is a c, a constant multiplied by n, so what about, when n is 0? So when n is 0, then t of n should also be 0. But there's no way that the algorithm will take exactly 0 seconds, right? Because at least the minimum that it has to do is to do this check. And that is not 0 time. So if you're really picky, then the function of t of n is really c times n plus some sort of fixed cost plus another constant. Okay, but again, this constant here, f, is also not important, because when n grows really big, then f is going to become so insignificant that it really doesn't matter. So c of, and that is again because n, when it grows big, it's going to dominate the value of the function. Okay, so this is an example of algorithm performance, and how we can go about thinking, how much time it might take, and also how we can go about actually measuring